Assalamu alaikum everyone. Today I will discuss some concept related to different functional form in regression. So far we have just discussed with the linear regression function, and the linear regression function is like where we have x as linear variable and y as linear variable. If we want to apply the OLS technique, definitely we need to have a restriction that the model should be linear in terms of parameters and it can be non-linear in terms of variables. Right now we'll discuss some of the possibilities where we'll see that how the non-linearity in variables is involved and what kind of functional form we could have. If I just write down the one which we have already discussed so far in our course. So we have discussed the equation like we are working with functional form. This is the discussion on functional forms of regression equation. And right now we have discussed only one, which is y is equals to beta naught plus beta 1 x plus u. And if it is a multiple regression, then we can have like beta naught plus beta 1 x1 plus beta 2 x2 plus so on beta k xk plus u. This is what we have discussed so far, and what we are intending to that we are going to discuss different type of models. These include log models, okay, and it includes number 3 log lin model, okay, and then it includes lin log model, and 5th reciprocal model, okay, reciprocal model. So I'll go with some of the details regarding these models. My concern is number 1, and what is meant by what is interpretation of beta coefficients, okay, in each model. Second, I would like to go with slope, which is dy over dx within each model. And number 3, which model is more appropriate. So we need to see the criteria which tell us that which of these model is more appropriate, right? So the discussion will consist of these explanations. Let's start with the kind of models. So we have the first model is log model. So suppose if you have, let me take it down, okay, all right. So we have like let's say we have a model let's say we have a model number 1. Suppose I have equation like y is equals to a into e raised to the power this one. Suppose we have labor raised to the power alpha and capital raised to the power beta. So if I just an e raised to the power u, suppose I have this equation. So it looks like non-linear equation because the parameters are as a power, coming as a power. So if I just take log on both sides, ln, so I'll take the log of this side as well, which is L power alpha, K power beta, E power U. And you know that the rule of log is that when it's applied to a product, it just applies to every term and it's being added. So I'll apply this way, it will become log of A plus alpha will come down, and that will become log of L plus beta will come down, and this become log of K, and U will come down, and it become ln of U, ln of E. And you know this value is equals to 1. So practically the model becomes ln of A plus alpha, ln of L plus beta, ln of K plus U. And this side is L and Y. So let's make it Y star. Let's make it beta naught star plus alpha, let's make it L star, plus beta, let's make it K star, plus U. So what is beta y star? Y star is ln of y. This is ln of A. This one is ln of L, and this one is ln of K. So if I look at this model, now it has become a linear in terms of parameters. It was already a linear in parameter, and now it is also linear in variable. If I just try to plot some kind of function of Cobb-Douglas type, so it looked like this. If I have labor here and capital here, and if just plotting the model in terms of labor and capital, I will have this kind of equation, y. Okay, the variable y will be looking like this, and it's not straight line, it's not linear. But if I change the axis with ln of L and ln of K, what will happen? This equation will become straight. And once it becomes straight, it can be estimated by the technique called OLS, right? Given the assumption that it satisfies all the CLRM assumptions, classical linear regression model assumptions. So practically what we'll do, since we are using the technique of OLS, we really need a model which is linear in terms of parameters. It does not matter if it is non-linear in terms of variables, just like ln of L and ln of K. We'll get the straight line, and if it is a straight line, we can estimate the parameters through the OLS regression. So that's what we will be working on, that there are different kind of models, and then we'll see that how can we estimate it. But before estimation, we'll try to learn that if we have a model, then what kind of parameter it has and what is meant by parameter. Does the parameter still is defined as slope, and it has some different meaning? So let's focus on it, that we have different kind of equations in terms of different functional form. Our focus is to see what is meant by the coefficient, which are the parameters, how to explain the slope, and the parameter in its original form, does it represent the slope? It's different. And the last topic which we'll discuss is that in this situation, which model is to select, and what is the criteria to select from within the models if we have multiple options. Now in front of you, there is a table which I have taken from your book of Gujarati, and it contains different kind of model. If you look at here, if you look at this, so if you look at the first one is the linear one, and it is simple as you have estimated earlier. Y is equals to beta 1 plus beta 2x, and then I will discuss it later, but just have a look at the model shape. Log linear, so log is written first and then linear. So look, the y is coming with ln, whereas x is coming also coming with ln x. So this is called that we have converted this model into linear by taking logarithm. That's why it's called log linear, right? The next model is log lin. Log means y variable. The first description is about the type of the dependent variable, and the second description is about the type of independent variable. So log lin means that y would be with logarithm, and lin means x will be linear. So log of y is beta 1 plus beta 2 x. Then log, that means the y will be linear, and log x will be with log. So y is equals to beta 1 plus beta 2 log of x. And reciprocal means that we have one of the independent variable is given in terms of a reciprocal. Reciprocal means that the variable is given as 1 by x. So practically y is equals to beta 1 plus beta 2 1 by x. This is another way the model can be defined. And then look at the last one, log reciprocal. This is log of y. Beta 1 minus beta 2 1 by x. So y is given in terms of logarithm, whereas x is given in terms of reciprocal. So these are the type of models which we'll deal with, and we'll try to understand what is meant by beta 1 beta 2 in this each equation, and how we can interpret it. And there are two things which we'll focus on, the slope thing and the elasticity thing. So move on and see that how we can take it. I will start with the first model, which is log linear model. I already have discussed with you that how we converted a Cobb-Douglas functional form and converted into linear by taking logarithm on both sides. So this kind of model actually was generated from that kind of equation. And it has a great deal. It has a great discussion, and it has a lots of feature That's why we generally consider Cobb-Douglas functional form is very, very important. So we'll give special attention to its coefficients, that if there is a Cobb-Douglas production function, or if there is a Cobb-Douglas utility function, how we can convert into a linear model taking logarithm on both sides, and then once it is done, then what is meant by beta's coefficient in that converted model, and if we are looking for the slope of that model, how we can calculate it, and what actually the coefficient and meaning is this in this model. So let's start with the log linear model. So I'm taking my word notepad, log linear, which is ln of y is equals to beta 1. So let me write down here log linear form, the first one. That's log linear. Log linear means that the form is converted into linear by taking logarithm. So what was that form? Log of y is equals to beta 1 plus beta 2 log of x, right? This is the regression model, and if I write regression, I will have to put u here. And regression line, what is regression line out of it? It is like ln y estimated is equals to beta 1 hat estimated, beta 2 hat estimated, and log of x. This is what we have as a regression line. So everybody understand that, right? So let's say if I take derivative. So if I take derivative of log of y, okay, and derivative of log of x, if I just take the derivative of this equation, forget about this estimated value, because it's just a understanding that the values are known. Let's make it log of y just to avoid some confusions. Let's make it log of y. So d log of y, derivative of this equation with respect to derivative of log of x. So what is it? Simply it's beta 2. Yeah? Beta 2 or beta 2 hat. Now if you look at the left side, this d ln of y, if we use the laws of derivatives, so it will be 1 over y into dy. This is the way it is being explained, and this is 1 over x into dx. And this time this side is beta 2 hat, right? Now if you just simplify this side, I'm writing it over here. So that will be dy over dx is taken separately, and this side will be beta 2 hat into, if you just take it on the other side, so it will become x by y. So this is what is it? This side is the slope. Okay, this side is the slope, because dy by dx is the slope. So if I have equation like this and I'm looking forward for the slope, so slope is not only beta 2 hat, it is beta 2 hat into x by y. Sorry, this should be capital, right? And if I just want to take what beta 2 hat is, so I just shuffle these numbers on the other side. So what we'll have, beta 2 hat is equals to, this side is dy over dx multiplied by, if I shift this term on the other side, it will be inverted, and that will be y over x. So practically there were a little mistake in the conversion, so I just corrected it. So practically dy by dx is equals to beta 2 hat into y by x. And if I just try to figure out what beta 2 hat will be, the beta 2 hat, so I'll have to shift this term on the other side, that will become dy by dx into x by y. So if you look at this side, what is it? It is the elasticity of the variable y with respect to x. So practically what is the message of this model? That whenever you have a model in which y and x both are in terms of logs, then the coefficient is not the slope but the elasticity. So basically if I explain what is beta 2 hat, so beta 2 hat is equals to percentage change in y with respect to percentage change in x, which is the definition of elasticity. Now you can explain in terms of all the equation in terms of any of the variable which will be given for the variable y or x. For example, if y is representing the production and x is representing the labor, so beta 2 will represent that if I increase in the production process, if I increase the labor by 1%, that how much percentage change will be in the production will take place, that is beta 2 value. So this model is very famous because now the coefficient are directly representing the elasticity, and if we are using any other model instead of this model, so in that case, if you're trying to get the figure of elasticity, in that case we'll have to figure it out and we'll have to calculate it. But in the model, when we have logarithm of y and logarithm of x, then every coefficient is not a slope but an elasticity. And in case so elasticity is a relative change, whereas, or the percentage change, whereas dy by dx, which is the slope, is the absolute changes. So once we are explaining beta 2 hat, we'll say if x is increased by 1%, then what is the corresponding change, percentage change in y, that is beta 2 hat. Whereas in order to explain the slope, we will say if x is increased by 1 unit, that what is the corresponding change into dy, or how much units the y will change. The answer is beta 2 hat into y by x. So this is quite ambiguous to explain until and unless we have a number. So moving on, we are done with this log linear form. The next form which I want to discuss is lin log and log lin. So move on. Let's have a look at the second form which we want to discuss. So we have discussed the linear one and we have discussed the log linear one. Now I'm moving on to the log lin form, and the two things which I will be focusing on is that what is the slope and what is the coefficient beta to represent here, and how we can get the slope or elasticity from there. That's what we are working on. Now you can look at the model number 3, which is log lin form, and this is log of y, which is equals to beta 1 plus beta 2x plus u. So you can see that log y is given in terms of log, where x is given as a linear number. So if I just take the derivative of both sides, so differentiating this equation with respect to x will be derivative of log of y over d of x, and that is answer is nothing but beta 2. So beta 2 is basically this ratio, where whenever we are taking the derivative of logarithmic term, that shows the relative change. So if relative change in y, relative change or the percentage change is the same, except that we just multiply it with 100. Relative change in y over this delta x is called absolute change. Absolute change in x is equals to beta 2, right? So whenever we are taking the d on a log of y, that is a relative change, because whenever we are explaining d ln of y over d of x, which is given as beta 2, and I want to expand it, that would be 1 by y into delta y dy, right? So that's why it's called relative change, because delta y is equals to y2 minus y1, so over y1. So basically numerator is a relative change and denominator is a absolute change. Now if I this is the meaning of the coefficient in this model. I just wanted to see that what is meant by beta 2. So beta 2 is nothing but the relative change in y over absolute change in x. If I just multiply it with 100, so that will become the growth, right? Because dy over y into 100, it is the growth rate of y over absolute value of x is equals to beta 2, right? So what does it mean that if I want to explain that what is beta 2, so beta 2 is nothing but let me write down beta 2. What beta 2 represents? Beta 2 represents that if there is 1 unit change in x, then y will change beta 2%. So what does it mean? Denominator is changing in terms of percentages. So this is the explanation of beta 2, but we are also interested to know that if we want to get the slope out of this model, how do we get it? So let's move on and see how we can take it. So if you see there, that is like what was the d, we had a slope like d, we had a slope d ln of y over dx is equals to beta 2, right? And what we are trying to see the slope out of it, which is nothing but dy by dx. So I just explained it, that is like 1 by y into dy over dx is equals to beta 2. And if I simplify it, so dy over dx is, so this y will go down and will be multiplied here. So see, beta 2 is not the slope, but beta 2 into y will become the slope, and when it will happen, it is log linear form. Whereas if we have model like y is equals to beta 1 plus beta 2x, so the slope is nothing but dy over dx is equals to beta 2. Yeah, we have done it earlier. And if the model is log of y plus beta 1 plus beta 2 log of x, in that case d log of y over d log of x is equals to beta 2. And if you want to see the slope, then dy by dx is equals to beta 2 into x by y. Remember, I just did it. And similarly, if we have a model, this is equality. If we have log line model, log of y is equals to beta 1 plus beta 2 log of x, then d log of y over, sorry, this was x, d of x is equals to beta 2, and that was dy over dx is equals to beta 2y. Got it? So in all of the models, what we are doing, we are not only trying to see what is dy by dx, but we are also interested to know what is the explanation of beta 2 or beta's coefficient in each of the model. And remember, the explanation could be simple slope. The explanation, if it is a linear model, the explanation could be the elasticity. Beta 2 is elasticity in case of both are logs, log model. And the explanation could be growth rate of some variable based upon some unit change in the independent variable if the model is log line, right? So we have discussed the three possibilities of the model, and let's have a look at the model again. What kind of model? So look at this linear model, you already done with this. Log linear model, you have already done with this, the slope and the elasticity. Look, log line, which is this one, and we already have done with this model that the slope is beta 2 into y and the elasticity is beta 2 into x. And similarly, lin log and baki, all these models you can do it yourself, that what these models are for. Now, having this understanding that we have different kind of models and we can have a particular interpretation of the slope thing here, and we can also work out with the elasticity, and we are interested to know what is meant by the beta coefficient and what is elasticity in every case. So moving on, that the next purpose is to see that why actually we go for it and why is the need of these kind of model. So well, that depends on the kind of theory. If it is a Phillips curve, definitely you can't take a linear equation. In that case, you will have to have a reciprocal equation. So that all depends on the type of the theory, which kind of model you will have. And sometimes we try different kind of model on a data to have a best fit. And remember, the meaning of best fit is always meant that summation ui square is minimized. So if suppose I have an option that whether I want to go with the linear model or log linear model in the first one or the second one, then what is the criteria to decide between these two models? Well, most of the people say that the criteria to decide between these two models is to see that which model represent high R square value, but that's not the right answer. The right answer is that it has certain criteria to be satisfied. Number one, whenever you are having a model and you are estimating OLS, using OLS to estimate the parameters, the most important thing is that your model must satisfy CLRM so that you can easily apply OLS technique. This is first pre-req to apply OLS. So you just have to really see that whether your model satisfy these conditions. Number two, you would have to see the sign and the magnitude of these models coefficients. For example, if your model is representing a demand theory, so you know that demand theory we just generally take a linear line downward sloping. So practically it means that a linear equation, just like first one, y is equals to beta naught plus beta 2, x is a demand equation where y is quantity demanded and x is prices, and beta 2 is the slope of the demand equation, which is just a linear number. But more practically, if you look at the right demand function, it's never a straight line, it's a convex line because of diminishing marginal utility theory behind. So basically in that case you would have to go with the reciprocal equation, which will give you a shape which is like convex type of figure. So question is that how do we decide that which model is to take? Well, answer is, first, whichever the model you take, you have to have a confirmation that it follows CLRM. Second, whatever the model you take, it must have the coefficients should be given in terms of right magnitude, and the sign should be according to theory. So more focus is on theory instead of type of equation. So if any of the equation will go with your theory, you can take it. And the third is that we should look for the individual significance. So if suppose you have chosen two models, so you will see that which model presents that the coefficients are significant based upon t-test, based upon 2t rule, based upon p-values. So that will make you decide that which model has more significance in terms of individual coefficients. Similarly, you also look for the significance overall level. For that, you will go with the F test and all the stuff which we have done already. So you just also have to work on and to see that whether your model fits for overall significance or not. And the last thing which you will see that is it that what is your R-square value. Definitely this is one of the parameter which makes you decide that which model to select. So any model containing high R-square is preferable in comparison to the one which is having low R-square, given the fact that both the models satisfies for sign and magnitude according to theory, individual significance, and the overall significance. If both models satisfy this criteria, then we definitely compare which model contains high R-square, and we definitely will go with the model which has more high R-square. So if you just look at this model, this is linear model where pi represents the inflation, the change in inflation, and this is unemployment. So this is basically a Phillips theory, inflation and employment relationship. And the first model is a linear model, and the second model is a reciprocal model. So all of the students who are from economics, they are familiar with the Phillips curve, and they also know that there is not a straight line, but generally it's a U-shape convex type of equation. So for any convex equation, the right model seems like 6.7.6. Actually, I have taken it from your book of Gujarati from chapter number 6. So if you look at the first equation, look at the t-values. Both of the t-values show that individual significance is there. Look at the R-square value. R-square says, well, 31% of the explained variation out of total variation. Look at the second model, the reciprocal model. And if you look at the sign, so here we go, the sign of beta 2 coefficient, which is for plus 18 points. So what it says, if unemployment goes up, 1 by UN goes down, so inflation will go up. So as per sign is positive is true here because it satisfies the theory, just like the above equation where unemployment and inflation are negatively related. In the second equation, it's also by the virtue of the type of the model, since your unemployment is given as a reciprocal, so positive sign is actually right here. So it shows that any increase in unemployment will actually going to reduce inflation. So as far as sign is concerned, both models are true. Look at the significance. So if the significance of the first model, linear model, constant had a significance 3.9 t value, whereas the second t value is lesser but still significant as per 2t rule. Similarly, if you look at above linear equation, the coefficient of unemployment was significant minus 4.06, whereas in the lower model is 3.06. So both of the models satisfy the significance. And if we compare the R square, the first model has 31%, whereas the second model has 20%. So apparently, in terms of the test of significance, in terms of R square, the model number 1 linear model outbeats the reciprocal model. So in this situation, we'll pick up that the data which we have selected actually is more better fitted to the linear model instead of reciprocal model. So these are the kind of small tips to compare the models and to see that which one is the right one. So in this situation, it seems like that the linear model is the right one. Which model select in which situation, that is a matter of theory, that is a matter of significance, that is a matter of R square, and that is a matter of which model suits the data best. So that is all from the functional form discussion. So practically we are done with all the chapters from the Gujarati book since till chapter number 8, and my next topic would definitely be from the multicollinearity problem, which we have already discussed partially in the class, but I will go with the details in the video later on. Thank you.